Trust boundary, drawing the lines your systems depend on. Security protocols, cloud infrastructure, and the AI working behind your tools, drawn out step by step until they click. Today on Trust Boundary, what actually happens when you type a URL, the DNS lookup that turns a name into an address from your browser's cache all the way to the root. You type example.com and hit enter, but no packet can be sent to a name. The internet routes to addresses. Meet the lookup chain, your browser and operating system with their own little caches. A recursive resolver, usually your ISPs or a public one, that does the real legwork. And the name server hierarchy, the root and top-level domain servers that hand out directions, and the authoritative servers that actually hold the answer. Before DNS existed, the entire internet's name-to-address map lived in a single text file. Every computer downloaded that one file from a single site to know what any name meant. As the network grew past a few hundred hosts, that stopped working. The file was always stale and always growing. In 1983, DNS replaced it with a hierarchy. Every zone runs its own name servers, answers are cached everywhere with a time to live, and no single file or machine is the bottleneck. That's what your browser used a moment ago. First, the free checks. The browser looks in its own DNS cache. Miss, the operating system checks its cache in the host's file. Ms. again, this name is cold. So your machine's stub resolver sends one question to its configured recursive resolver. What's the address for example.com? Then it just waits. The resolver does everything else. The resolver checks its own much larger cache. If anyone nearby asked recently, the chase ends right here. Today, a miss. So it starts at the top, one of the 13 named root servers, each really hundreds of machines around the world. The root doesn't know example.com, but it knows who runs.com and answers with a referral. Same question, one level down, to the top-level domain servers for .com. Another referral, here are the authoritative name servers for that zone. Third hop, this time to a server that actually holds the zone's records. And an answer at last, the address record stamped with a time to live chosen by the zone's owner. The resolver caches it, hands it back, and your OS and browser cache it too. The whole cold chase often takes well under a couple hundred milliseconds. Now, and only now, the browser can open a connection to that address. What happens on that wire is a story of its own. Every answer DNS returns is a resource record, and it's just 5 fields in a row. This one maps a name to an address, the name being looked up. The TTL, how many seconds every cache along the way may keep this, 1 hour here. This single number is why DNS changes feel slow. The class, effectively always IN for internet. The type means an IPv4 address. And the R data, the actual answer this record carries. Change only the type, and the same 5-field shape carries everything else in DNS. IPv6 addresses, aliases, mail servers, the name servers themselves, and the text records behind email security. Here's the nightmare. If an attacker can get your resolver to cache a forged answer, everyone using that resolver goes to their servers with the correct name in the address bar. It works like a race. Your resolver asks the real name server and waits for a reply. The off-path attacker can't see that query, so they flood the resolver with forged replies, guessing the details, hoping one lands before the real answer. But the resolver only accepts a reply that matches the query's 16-bit ID and the source port it used. Randomize the port, and that's roughly 4 billion combinations to guess blind. In practice, the real answer, what does match, usually wins the race and gets cached. The forgeries are dropped. That entropy is a lock on the door, not a wall. The real fix is DNSSEC. The zone signs its records, and the resolver verifies the signature. So a forged answer fails the math, no guessing required. One more thing the classic story leaves out: for 40 years, those queries went out in clear text. Anyone on the path could read or rewrite them. On classic port 53, your queries are visible to your ISP, the coffee shop Wi-Fi, every hop in between, a full log of every site you visit, and a chance to tamper with the reply. DNS over HTTPS and over TLS wrap the same query in encryption to your resolver. The path now sees only ciphertext. Though note, your resolver still sees everything, so you've moved the trust, not removed it. Most browsers and operating systems now support this by default. Every hop that saw the answer kept a copy. your browser, your operating system, and the recursive resolver. Each copy lives exactly as long as the record's time to live allows. Here, 1 hour. And then it must be fetched fresh, which is the real reason DNS changes seem slow. Nothing is being pushed anywhere. The old answer is just waiting to die, cache by cache. Step back, and every DNS lookup is a chain of trust. You trust your resolver to answer honestly, which is why which resolver you use is a real security choice. The resolver trusts the referral chain from the root down. DNSSEC is what lets it verify that chain cryptographically instead of simply believing it. And every cache trusts the TTL. That number is the freshness contract for the whole system, and the honest reason a DNS change takes time to propagate. That's one boundary drawn, and there are plenty more lines to trace. If this made things click, subscribe, and here's what we're drawing next.